Thank you very much for the introduction, and thanks for sticking around. So I'm going to talk about the numerical approximation of traces of matrix functions. So this is like a numerical linear algebra talk. It has no quantum and no optimal transport in it. But I hope the techniques that I will talk about will be useful for those of you working on more on the numerical side of quantum optimal transport. And I'll try to point out some connection during the talk. So first of all, let me clearly define what the problem is, what we're trying to do, and to fix some notation. So what do I mean by a matrix function? Well, you can think about any scalar function f. And if you have a matrix B, let's say a real matrix, doesn't really matter that it's real. I just want it to be square, size n by n. We can define the matrix function, we denote it with f of b, using a diagonalization of the matrix. So
we assume that the matrix is diagonal.
Okay, I knew that some mathematician would shout at me for that. So okay, so you can actually do it. Okay, so in this talk, our matrix B will be symmetric, so it's diagonalizable. Now, if the matrix is not diagonalizable, you can still define a matrix function using Jordan canonical form or other things. But let's stick to a simple definition. If B is diagonalizable, then you can take an eigen decomposition, and then you can define f of B by basically taking the f of the eigenvalues of the matrix. Okay, so this is a definition, but the problem is if you would like to compute this, if you really want to use an eigen decomposition, that's pretty expensive to compute. Okay, so, and the goal of this talk is to discuss algorithms to approximate the trace of matrix functions. So if you think about it, the trace of this guy is just a number, so you can hope for something a bit quicker than just, going through diagonalization, computing the whole matrix function, and then just taking the trace. So first of all, let me give you some motivation for this problem. So we've seen this week in several talks, for instance, by Natalia, by Lorenzo, by Marvin, that sometimes in regularized quantum optimal transport, at some point you have the trace of the exponential of some matrix, which is really huge. But has the nice property that you can quickly multiply it with vectors. So this is the setting we want to look at. So computing traces of matrix functions, assuming that the thing you can do with the matrix is matrix vector multiplications or quadratic forms. Now the algorithms I'm going to talk about are not really restricted to the exponential or to that setting. You can think f as the function f to be whatever you want. In particular, here I listed some kind of interesting functions that people use, for instance, the entropy, the logarithm, the inverse, powers, and even weirder things like step functions. So this is the outline of the talk. So in the first part, I would like to present a randomized algorithm for trace estimation. Let's say forgetting for a minute that we actually want the trace of a matrix function. We'll assume that we want to approximate the trace of a matrix A, which is symmetric. And we assume that we can do matrix vector multiplications with A or compute quadratic forms with A. Okay. Now, in the second part of the talk, we actually remember that we're interested in trace of matrix functions. So we'll tell you how you can approximate matrix vector products with the matrix functions or quadratic forms. And then in the last part, I will discuss some variance reduction techniques for this problem. Please feel very free to interrupt if you have questions or if the notation is not clear. Yep.
Very quick question.
Yeah.
Is there almost no difference, but do you want the trace of A or the normalized trace of A, but you divide by 1 over this?
I'm I'm generally talking about the trace. I have some results like for like relative error for the trace, but yeah, in general, it's really just a trace and a bit of partial trace. I'll say something about that as well. Okay, so let's dive into trace estimation. So now the setting is we have a matrix A. Think of A being f of b, but now A is just A. It's a symmetric matrix of size n by n. We want to approximate its trace. We assume that the only thing we can do with A is quadratic forms. Because if we had the actual matrix A in our hands, computing the trace would be just a stupid problem. So what one could do, so one thing you can do is, okay, like if you take the vectors of the canonical basis, like for instance, if you take the vector 1, 0, 0, 0, 0, and you compute a quadratic form with this, of course you get the first diagonal entry. And then you could do this with the second canonical basis vector and so on, but there's n of them. Think about n being large, this is too much, okay? So the cool thing is you can obtain approximation of the trace a bit faster using random vectors. So so this is what's called the Hutchinson trace estimator. Actually, it was proposed by Girard a couple of years earlier, but people tend to call it the Hutchinson trace estimator. So this is based on the fact that if you take a random vector x of length n, which is isotropic, so the expected value of the rank 1 matrix x transpose is the identity, then the expected value of the quadratic form x transpose ax is exactly equal to the trace of A. And this is really nothing magical because if you write down what this expectation is, you can, this is a number, but you can just write it as the trace of that number. And now you can go, I think, okay, maybe I chose a bad place to write. I'll go here. You can use the cyclic property of the trace and put the x transpose on the other side.
N missing. Because the expected value of the identity. So if you had the identity somehow, then you would come. I mean, the trace of identity is n, right? So in this formula, there's an n missing.
You need to take a trace there, no?
Wait a second. Okay.
If you multiply the first one by n.
No, she has it. X transport is right.
Oh no, that's sorry. This is a number, so like x is a vector. Okay.
Oh, okay,
let me do it like
you're
this.
right. I'm sorry. You're right.
I'll write it out. Okay, so this is the expected value of the sum over I and j that goes from 1 to n, the size of the matrix of xi, a, ij, xj. Okay, so now the bilinearity of the expectation, you can put the sum outside, and now you get.
What you had before was totally correct.
Yeah, I just got.
Don't let any person change that.
It's like a one-line proof, okay?
Yes, and it's totally correct.
Yeah, you can view it in this way. This is aij times the expectation of xi, xj. And now this guy is 1 if and only if I is equal to j, so the only terms that survive are the ones from the trace of A. Okay. So, of course, if you only take one random vector, your estimate, and you take x transpose ax for one choice of random vector, will be super noisy. So what you do, you take a bunch of copies of independent copies of this random vector, you compute the quadratic forms, and then you average. So this is what we call the Hutchinson trace estimator.
Alice, did you also say that you probably need capital N of the order log n or so, right? I mean, that should be enough.
I will tell you exactly what that capital N should be later. So first, let me say something about this, what assumption we want on this random vector x. So the assumption we want is kind of very general. What people do commonly is, for instance, to choose random vector, like, so I would say the two most common choices for the random vectors are Gaussian random vectors, in which you just take each vector to have IID entries, which are standard Gaussian random variables, or Rademacher vectors, in which you take each entry to be plus or minus 1 with probability 1/2, all independent from each other. And you can actually, I will not do the computation because I will mess up, but you can compute the variance of this estimator. And in the case of Gaussian random vectors, the single sample, like the estimator with one single sample, has a variance of twice the squared Frobenius norm of A. With Rademacher vectors, the nice thing is that the variance is a bit smaller, and it's basically twice the Frobenius norm of the matrix that you obtain by zeroing out the diagonal of A. So equivalently, like, this is nothing magic, but like if you take a diagonal matrix A and one Rademacher random vector, you recover the trace exactly. Okay. I will mention in a couple of slides that actually in some cases you might want different distributions for the vector x. But yeah, so think about these ones for now. So how does this estimator behave in practice? Well, here is an example. I took a matrix A. Yep.
Sorry, I missed it in the previous one. Sorry if this is really clear, but with variance, you mean the variance then on the trace of A?
Yes.
Okay.
Yes. So it's an unbiased estimator, and that's really the variance.
So you can get into some pathological situations.
What do you mean?
When A is like not well constrained.
Is not what?
Like well posed or well identified. Like are there instances of A where the variance will become like really, really large?
Okay, so maybe I misunderstood your question, but like here A is fixed, and the randomness is on the vector x.
Okay, yeah. But
So,
the variance in the end will depend on the structure of A.
yes, it depends on the structure of A.
So not so much on how you choose
The
sample the x's.
No, it depends on the axis as well. So this result is for Gaussian random vectors. This result, it has a different variance.
Depends on the distribution.
Yeah, it depends on the distribution. It depends on everything. It depends on the distribution, and it also depends on the matrix A. And if you know something about your matrix A, you may want to try to get some random vectors that are better for that kind of A. I'll give you an example of that later. Okay, so, yeah.
The Frobenius norm is just like the square of all values in the matrix, right?
Yes. So the Frobenius norm. Trace of A transpose A, or sum of Aij square.
Okay.
Okay.
So are the Rademacher vectors just strictly better than the Gaussian vectors because you took out the diagonal of A, so it's just fewer entries to square?
Yes. But there are reasons for preferring Gaussians sometimes. Like, they're easier to work with. For example, if you want to prove something, Gaussian vectors are much easier. But yeah, so you can, I'll show you an example later. You can see a tiny difference. Yeah. Okay, so back to this example. So what's happening here is I took one matrix. It doesn't matter what matrix it was, because it's like the plot is going to look the same for any matrix I choose up to translation. And I'm looking at the error of the Hutchinson trace estimator, so this guy over there. When I increase the number of samples, capital N, and the red dotted line is 1 over square root of the number of samples. So, yeah.
Yes. What is the size of this matrix? I mean, it's much bigger than 10 to the power 6.
No, it's not. This matrix was actually quite small, because otherwise my laptop would explode.
But that
that doesn't make
translate
sense.
very, very seriously in what you get. Like, for example, suppose that the matrix A is like 3 by 3.
Yes, so actually
You wouldn't get this plot.
you would, yes.
You would.
You would, because, so this matrix, I think it was 1,000 by 1,000, something like that. It is because, like, even when, okay, so first of all, let me tell you, so if you need a number of samples which is larger than the size of the matrix, then you should not use this algorithm. It doesn't make any sense, right? Because you could just take the diagonal. So this is really just for illustration purposes, okay? But the thing that really matters, it's not the size of A, but it's the Frobenius norm for the variance. So, I mean, you can think, like, if your matrix is bigger, maybe also the Frobenius norm is bigger. So in that sense, it matters. But otherwise, like, there's no explicit dependence on the size of the matrix in what I'm showing you. Hope that answers the question. Okay, so so what you can see is, like, the error oscillates a lot. This is a log-log plot in case it's like the numbers are too small. But what one can ask is, okay, like, if I want to have an estimate with a certain accuracy, epsilon, up to some failure probability, how many samples do I need to take? And there are various results on this, both for symmetric positive definite matrices and for symmetric indefinite matrices. So let me go slowly through this slide. So if your matrix A is symmetric positive definite, then you can actually look at the relative error, okay? Because you're sure that the trace is positive, so you can divide by the trace. And there's this result here that says that if you take Gaussian vectors, and if you take a number of samples which is larger than 8 over epsilon squared times logarithm of 2 over delta, then you get accuracy epsilon, like relative accuracy epsilon, up to failure probability delta. So, and you have something very similar for the macro-random vectors, you just have a different constant, which is really, yeah, don't look at the constants, okay? So there's one good thing and one bad thing. So the good thing is the dependence on delta. So it has a logarithmic dependence on delta, so you can make the failure probability really small if you like, without increasing the number of samples too much. The bad thing is, of course, the epsilon square in the denominator, because it means that you need, yeah, a number of samples that grows like 1 over epsilon square is a lot. So that's also the reason why I will discuss some variance reduction techniques towards the end of the talk. So this is the symmetric positive definite case. The symmetric indefinite case, well, there's no hope for there's no hope to get a relative error bound, just because if your matrix has trace 0, you cannot divide, and also, like, the estimator will not give you 0, will give you something. Okay, so the best thing you can do is to get some bounds on the absolute error, and now the bounds, so the number of samples depend again on this. They still have this logarithm of 2 over delta. They still have this epsilon square in the denominator, and they also depend explicitly on the Frobenius norm square of the matrix, plus some term which we can ignore. Yes?
Yeah, sorry, I'm not a mathematician, so I probably very stupid question.
Go ahead.
Why there is not a dependence on the size of the matrix A?
Okay, so I understand how that can be puzzling, but, like, it's somehow encoded in here, okay? So if you think about, I don't know, think about the identity matrix, it's maybe the simplest one. If you look at the Frobenius norm, it grows with the size of the matrix, right? So if, like, that term will be bigger if your matrix is bigger.
But on the first case, you don't have that.
You don't, because think again about the identity matrix. What happens to the trace? It also grows. Okay, and that's in the denominator. So somehow these things cancel each other out.
So
Yep.
let me just try and follow that up. I mean, you can think of a very naive algorithm for getting any matrix function, which is simply to do Given's householder on the matrix. It costs you n dimension cubed, and then you can do anything you like, right, if you got it into diagonal form.
Say it again, sorry.
You could bring the matrix to diagonal form at
Yes.
the cost of cubic scaling.
Yes, but I don't want to do cubic
No,
scaling.
so, but this is going to cost quadratic for every sample you take. So the real question is, for a given accuracy, is the number of samples you need to take less than n to the power 1? Otherwise, you could just do it in spectral form.
Yes, so the idea is that you want this n, yes, so you want this capital N to be smaller than the size of the matrix, smaller than small n.
Yeah.
That's the thing, yeah.
I think maybe there's a confusion, which is that in your methodology, the application to a single vector is free. It's one operation, right? The
Yes,
evaluation is
yes,
one
yes.
As opposed to n squares.
Yes, that definitely. And like if you think about one matrix vector multiplication actually being a matrix vector multiplication with f of b, then it's even more expensive. But yeah, so the idea is, I'll get to you. The idea is, this is the theory that tells you how many samples you need. This makes sense if your matrix is really large and you want to do maybe 100 samples or something like
So
that.
epsilon and delta are both scaling with the size of the matrix, I guess. No, epsilon is not, but delta, they're intensive, right?
I mean, that's something, okay, let's maybe stick to the symmetric positive definite case. So this works for any matrix. Okay, so if the size of the matrix grows, this still holds.
So epsilon, your target accuracy should be independent of the dimension of the matrix, because you're dividing by the trace.
Yes.
And delta is, of course.
Then,
probability.
of course, if you really use this algorithm inside some computations, you can choose your epsilon, and that can depend on the size of the, like, you can choose it as you wish.
So for the positive definite case, it really is quadratic in the size of the matrix, but for the non-positive definite, it's not. Is that what all this means?
I think you can view it that way, yes. So, but yeah, so the thing you have to keep in mind is, I expect that if the matrix, like if the size of the matrix grows, then also the trace may grow. And here, this is not reflected by the epsilon. It's as if that epsilon, okay, no, this epsilon had the trace of A in it.
Right.
Okay, so
It's a different one to the one above.
could be, yeah.
Sorry to steal so much of your time.
No, don't worry. Yeah.
So, of course, my question, which is maybe partially an answer, is if you take an arbitrary distribution, not Gaussian, just only isotropic, I think there is dimension dependence, right? I think you need dimension dependence.
To do what? Like to have
arbitrary
some
distribution
concentration
was
results?
Gaussian, just expected value of XX transpose is 1. I think the dimension does kick in. I mean, Gaussians and Rademachers are just too good.
Yeah, I mean, for sure. That's why.
If you take an arbitrary distribution, I think the dimension does kick in. For
Right,
this.
but I have the choice of which distribution to take, so I'm going to take some simple one.
Well,
I
in
think
some
that's the.
situations you have.
You don't have a choice. Okay, fair enough.
Choice, and then
Fair enough.
You have to live what you have with, right?
Sure.
Then I think the dimension does kick in.
Okay, I'm not aware of any like concentration results like these for other kind of distributions, but for sub-Gaussian vectors, for sure, you can do a lot of stuff.
No, you can do it for an arbitrary distribution and still get estimate. That's very easy.
Okay, thanks. Okay, so this is an example of basically the previous bound for indefinite matrices. So let's stick maybe to one of the pictures. This is a symmetric matrix. Again, doesn't really matter what it is. And this blue line is the value of epsilon such that you obtain accuracy. Sorry, the value, yes, of epsilon such that you get that accuracy with 90% probability. And it's wiggly because like it's computed numerically. And this green line is the bound that I showed you on the previous slide. So what I want to say is it's kind of tight. Now, another thing that I mentioned is, also going back to your observation maybe, is you may not, like Gaussian random vectors and Rademacher random vectors are not always the right choice. For example, if you have some matrix which is where you know where most of the mass is concentrated, you may want to design a different type of random vectors. So one example that I can give you is the so-called probing vectors. So just as an example, assume that you have a three-diagonal matrix. Something like this. Well, basically, you can recover the whole of it just multiplying with three vectors, which are 1, 0, 0, 1, 0, 0, blah, blah, blah. 0, 1, 0, 0, 1, 0, blah, blah, blah. And 0, 0, 1, 0, 0, 1, and so on. So one thing you can think of is if you know that your matrix has, for example, so this is really just for illustration purposes. So if you take the exponential of a three-diagonal matrix, it tends to have a very strong decay when you move away from the diagonal. And then you can sort of design your random vector x to be something like this, in which you put plus or minus ones with equal probability, all independent from each other. You scale by square root of 3 just because you need that, and then you pick one of them at random. Okay, so this is what happens. So for that matrix, I plotted now this S should be capital N, the number of samples. So this is what happens to the average. I plotted the average error of the Hutchinson trace estimator applied to A using Gaussian vectors, Rademacher vectors, and this kind of probing vectors. So you see, for this specific example, the probing vectors are much nicer. And you can also see that little difference between the Gaussian and Rademacher vectors, which is due to the fact that the Rademacher vectors do not see the diagonal. Okay. Okay, so some variations on this trace estimation business. So what if A is complex? You can do the same thing. What if A is non-symmetric? You can do the same thing. The theory basically applies to the symmetric part of A. And what's maybe a bit more interesting for this audience is what happens with partial traces. You can generalize the Hutchinson trace estimator to partial traces as well. So let's assume that you have a matrix A, which is defined on some tensor product of two spaces, not more, because otherwise it's complicated to write. And you can, so like in this matrix, you have to think of each Aij to be actually a block, another matrix. And then one can write partial traces, for instance, by taking the trace of each block. And so the nice thing here is that if you tensorize a vector v with identity, and then you take the quadratic form, which now looks like a long matrix times a big matrix times a tall, skinny matrix, this exactly gives you a matrix containing, like a smaller matrix containing the quadratic forms with the vector v. So by what we said, if you take this, instead of this v, you take a random vector, which is isotropic. The expectation of this thing is exactly the partial trace you want. And to do the other partial trace, you just swap the order of the Kronecker product. And of course, like before, you should take a bunch of samples and then average, just not restrict to a single one. Now, of course, there's one bad thing, which is to compute one partial trace with even one sample, we actually need n matrix vector multiplication, if you wish, like to compute A times this guy. But I think the nice thing is that if you generalize to higher dimensional matrices, so like matrices defined on the tensor product of, I shouldn't have used capital N, but like many spaces, and you trace out everything except for one, the vector v gets, like this vector x or v gets longer, but the size of the block does not increase. So I guess this is good news. Okay, so this concludes the first part. Now I just want to tell you a bit about how you can approximate matrix vector products or quadratic forms with a matrix function, f of b, because this is what we need for the Hutchinson trace estimator. And I'm kind of going maybe a bit quickly on this, but I'll tell you how it works, not really why it works. But the idea is using Krylov subspace methods. So a Krylov subspace associated to a matrix B and the vector x. So the goal is to compute f of b times x. So the Krylov subspace associated to the matrix B and the vector x is the span of x, bx, b square x, blah, 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 until b to the m minus 1 x. And here you have to think of m being much smaller than the size of the matrix. Otherwise, it doesn't make sense. And well, for symmetric matrices, you have the Lanczos algorithm, which builds an orthonormal basis of this subspace, which has dimension at most m, using basically modified Gram-Schmidt procedure. And as a byproduct, you get a partial factorization, let's say. It's called the Arnoldi decomposition. So this um here is the orthonormal basis of that space. Plus 1 is the same thing when you add one vector. So actually, like the first piece, this piece, is exactly And so the product of B with is plus 1 times some matrix, which is small. And in the case, in the symmetric case, this is a three-diagonal matrix. Okay. So this is something that you can do by multiplying. So again, I want to stress that to get this stuff, the only thing you need to know is how to compute matrix vector multiplications with the matrix B. In particular, you need M matrix vector multiplications. And then you have the orthogonalization cost, which is like nm squared. Hopefully, it's something feasible. Okay. So now once you have this, how do you get an approximation of f of b times x? Well, you basically look for an approximation in the span. So that's a vector. You look at an approximation in the span of the Krylov subspace you have. So as an approximation of f of b times x, you can take times f of this km matrix, this small matrix, times E1. And this is basically saying that you're taking transpose B which looks like a sort of a compression of B onto the Krylov subspace you computed. Then you compute f of that. Now it's f of a small matrix, so you can do that via diagonalization or whatever you want. And then you make it bigger again by multiplying with transpose on the other side. Okay. And for quadratic forms, it's basically the same thing. This thing is really just this one where I multiplied x transpose to the left. And then operationally, what happens is you really just need to look at this km, evaluate the function f on this km matrix, take the entry in position 1, 1, and multiply by the square norm of x. Now, this may seem black magic. I'll say something about that in the next slide. But I want to emphasize that this thing is exact. Okay, so the first thing is exact if f is a polynomial of degree m. And the second thing is exact for polynomials up to degree 2m. So what happens is that these approximations are good, can be used and are good, if the function f is well approximated by a low-degree polynomial on the spectrum or the spectral interval of the matrix B. Okay, otherwise, nope. So there's a nice connection that I want to point out, a connection with quadrature. So regarding the quadratic form, so x transpose f of b times x, you can actually rewrite it as an integral. So this is here. So if you take a spectral decomposition of the matrix B, you can rewrite x transpose f of b times x as basically an integral of f with respect to a suitable discrete measure that has some suitably weighted deltas in the eigenvalues of the matrix. And now, of course, if you have an integral, you can do quadrature. And it turns out that what I told you in the slide before corresponds exactly to doing a Gauss quadrature rule to this integral. And yes, so this basically also tells you a bit more on why the method works and like for which kind of functions and kind of spectral intervals you can hope for that to work. Okay. Okay, so now we know how to multiply matrices with vectors. Sorry, matrix functions with vectors or computing quadratic forms. Let's go back to a minute to the Hutchinson trace estimator. So the main problem is that it's painfully slow to converge. So let me tell you a bit how one can address that. So let's go back to the setting in which we want the trace of a matrix A, and we know how to compute matrix vector products with A. Okay, and assume that someone from, I don't know, hands us a matrix AR, which is a rank R approximation of our matrix A. Okay, for some rank R much smaller than N. Now, why? Okay, so one thing we can do is to write the trace of A as the trace of this low rank approximation plus the trace of A minus the low rank approximation. And I mean, this is just by linearity of the trace. But now there are two things. So okay, there's a typo. So the first thing is that this term, the trace of AR, is easy to compute. Because normally when someone gives me a low rank matrix, they give me something of the form like BC transpose. Right, and then if I want the trace of this, it's just a trace of C transpose B, and that's a manageable matrix. And the second thing is that now, of course, I need to approximate or compute the trace of A minus AR. But if I want to use the Hutchinson trace estimator for that, its variance and also the bounds basically depend on the Frobenius norm of that. So hopefully, if this AR is a good approximation of A, the variance is much smaller. Okay. So is the idea clear or? Okay.
So you want to remove the projection of the maximum likelihood?
It can be something a bit more general. It can be a projection. Yes. So now, of course, the next question is, what do I take? I have to find this AR myself because nobody's giving it to me. So one thing you could do is to remove some, explicitly deflate a couple of eigenvalues. You can also do something a bit more, less precise, let's say. So the important thing is that whatever we do just only uses matrix vector multiplications with A. So one thing you can do is also to compute a randomized low rank approximation of the matrix. For example, one way to do this is by the randomized SVD. So this means that you take some random matrix omega, for example, filled with Gaussian, IID Gaussian entries. And then you take the product, the matrix. So this is a product of A, big matrix, with this omega, which is like tall and skinny. Then you compute an orthonormal basis of that. Okay. You compute an orthonormal basis of that, and then let's call it Q, and then your low rank approximation can be taken as Q transpose A. So this is cheaper than making it converge to the first singular values, the first eigenvectors, sorry. There's also something else that you can do, that works pretty well for symmetric positive definite matrices. I wouldn't attempt it otherwise. It's called a Nystrom approximation. It has this form. It's basically the only thing you need is a so-called sketch of A, so the multiplication of A with some random columns. And there was a very interesting result by Meyer and collaborators that says that for symmetric positive definite matrices, if you take R random vectors for doing this, and then use R random vectors for estimating the trace of A minus Q transpose A, then the error is bounded by 1 over R, not 1 over square root of R like it was before. And of course, like this is somehow not optimal to divide the allocation of random vectors and matrix vector multiplications, like half for the low rank approximation part and half for the Hutchinson part. That's something I've worked on with David Persson and Daniel Kressner. We tried to, basically we tried to give an adaptive version of this algorithm in which after a couple of, you start multiplying with a small matrix here, and then during the algorithm, you try to understand how many samples you actually need. But okay, that's a bit, I won't go into details about that. I want to show you an example of what this variance reduction really does. So here I took a matrix with some, with singular values 1, 1/4, 1/9, and so on. So it's like they decay, but not extremely fast. And I'm showing, so the red line is the trace of the low rank approximation. Because one thing you could think of is, okay, I have a matrix A, I want to compute its trace. For this kind of business, I need to compute a low rank approximation. So why just not take the trace of the low rank approximation? So that's the red line. The blue line is pure Hutchinson. And then this combined technique is, which is called Hutch++, is this yellow line here. Okay. And here I want to emphasize, so the x-axis is the number of matrix vector multiplications with the matrix A. So that's somehow the kind of unit that I'm using to discuss the cost of this algorithm. Okay, so last thing. So let's not forget that A is actually a matrix function. So what's the problem with that? That computing one matrix vector product with A actually means many vector products with B, if you're using a Krylov subspace method to approximate f of B times a vector. So there are possible solutions to that people have looked at. For instance, there's a way to somehow reuse, so to merge two steps. So the computation of f of B times omega, which gives you this Q, and then the trace of Q transpose f of B times Q. That's something that can be managed. Another idea that I think is very promising is instead of looking at low-rank approximation of A, look at the low-rank approximation of B, and then try to incorporate that. Because to get a low-rank approximation of B, you really just need matrix vector products with B. This is super interesting. I think it only makes sense if f is increasing and f of 0 is equal to 0, or if you somehow can reduce to that case. Now, there's been some work on the partial trace, but from what I know, it's still, like there's not many people who looked at it. And there's, I just want to mention this paper here. So they look at the partial trace of the exponential, and there they really deflate the largest eigenvalues. They deflate the largest eigenvalues, and then they approximate the rest with the Hutchinson trace estimator. And this, yeah, this simplifies some things. Okay, so I'm on my last slide, so just to sum up a bit. So we can compute approximations of the trace of a matrix function if we're allowed to multiply with vectors and compute quadratic forms. And well, the theory tells us exactly that, like, if you're using exact matrix vector products or quadratic forms, the estimate is unbiased, the variance is under control, and you also have some concentration results, at least for Gaussian random vectors, Rademacher random vectors. And my hope would be that if you really are not super interested in the trace itself, but like you're using it inside some optimization algorithm or something else, then an approximation is good enough instead of really going through diagonalization every time. So for dealing with, third point, so for dealing with these quadratic forms or matrix vector multiplications, you can use Krylov subspace methods, and it's really linked to polynomial approximation of f on the spectrum of B. And there's a number of variance reduction techniques that you can try to make the convergence a bit faster. Thank you very much.